we use partial fractions if we are given an integral where the denominator can be factorized, or if we're given it to us in a form that's already factorized. So in this example here, we have 1 over x plus 3 multiplied by x plus 2. So in the denominator, we have these two linear factors that are factorized, which means we can use partial fractions. Another example that you might get is if you have 1 over, and then on the denominator you just have like a quadratic, like because here you can factorize the denominator and use partial fractions from here as well. Now, of course, the difficulty when we're given an integral like this is that we can't integrate it straight away because we have like a product on the denominator, right? We can't use linear substitution because we have these two linear elements. And we can't use nonlinear substitution either because we don't have like multiple different parts of the function that we'd cancel out. So what we need to do is use partial fractions. So we can solve this by splitting the fraction into two parts. So what you need to do is you need to get each of your linear factors and you need to put them on the bottom of the fraction and split them up into a sum with A and B on the top. And A and B are like constant real numbers, but we don't know what they are yet. So the utility of doing this is that now we have these two separate things, or two separate terms, I should say, rather, that we can then integrate. You know, we can use logs to integrate them, and we just have these like regular old constant numbers on the top. And we'll get into how, like, proving how this splitting of the fractions actually works. But this is what we can do now. It's really simple from here on out. All we need to do is find A and B. So what we can do is use a bit of cross multiplication and simultaneous equations to get the answer. And we'll get into an actual application of this in a second. But as a note, this technique only works when the degree of the denominator is greater than that of the numerator. So I think we'll get into an example of that as well. Okay. So in this example here, we need to find the integral of 1 over x plus 3, x plus 2. And we can split this up into two fractions as we did in the last slide, a over x plus 3 and b over x plus 2. And accordingly, a x plus 2 plus b x plus 3 is going to be equal to 1. So this is the equation that we can get the form of, and from here we can then find the values of a and b. So you don't actually need to remember how to get this necessarily. It might be more necessary for harder questions, but if you're just looking at like regular questions, you don't actually need to remember how to get this. But what you do need to remember is, of course, that like these are swapped. So the a is with the x plus 2 here, and the b is next to the x plus 3 here, but over here they are swapped. So that's just something that's easy to get mixed up. and just make sure that you're conscious of that when you're doing the question. But I will show you guys how we actually get to this equation without the fractions here. All we do is we do some cross multiplication. So if we have 1 over x plus 3, x plus 2, what we do is we multiply everything by x plus 3. Sorry. So we multiply everything by x plus 3. And then we multiply everything by x plus 2. And of course, this is going to cancel these out. So on this whole left-hand side here, we're just going to be left with 1. And on this side here, we're just going to be left with a x plus 2 plus b x plus 3, because all of the other components cancel out. Okay, so as I said, you don't need to remember that super in detail, but it is useful, especially if you're checking if the a and b are multiplied or divided by the right linear factors and you haven't mixed them up. Okay, so from here we are going to equate the coefficients. So we are going to get a plus b equals 0, and 2a plus 3b equals 1. And from here, we're going to use simultaneous equations, these two equations here, and we are going to find that a equals -1 and b equals 1. So from here, we know our a and b value, and so we can substitute them into this section here, which is going to give us our two partial fractions that we can then integrate.